Google Developer Student Clubs train hundreds of thousands of university student developers globally while having fun getting to know other students at their school. Google selects students with strong leadership skills from across the globe once a year to start a club on their campus. These leads believe knowledge is power and that technology can do extraordinary things for the world. They take on the responsibility to help students learn and empower each other to solve real problems around them. Students can participate in the annual Solution Challenge by Google developers to solve for one of the United Nations Sustainable Development Goals. Join us in building a global community for students in technology.
Okay, hello everybody. My name is Trevor. I'm a core team member of the Google Developer Student Club based in Zurich. Part of what we do as a club is to organize events with guest speakers. And today we are joined by Dr. John Cooper from NASA Langley Research Center. John focuses on autonomy for space robotics, and today he's going to talk to us about a project that's being done at NASA related to an assembler's project for assembling objects in space. Really happy to have John here and excited to see what he'll present. So thanks a lot, John, and you can take it away from here.
Yeah, thanks for the introduction, Trevor, and thanks a lot for inviting me. I'm John Cooper. I'm going to talk today about autonomy and robotics for on-orbit servicing, assembly, and manufacturing. We call this OSAM for short, OSAM. So OSAM is basically a new paradigm for how we deal with mostly large structures, but also existing spacecraft. The current paradigm is, things have to fit inside the launch volume of a launch vehicle. The James Webb Space Telescope is basically like the limit of the size of a in-space telescope that we can have. That's like a monolithic structure, right? To get any bigger, we'd really have to build the thing in space, and that's what one of the kinds of challenges that OSAM is addressing. There's also servicing of existing spacecraft, so upgrading and repairing, extending the life of them, and in-space manufacturing, which is kind of like building components out of raw materials in space. Most of what I'm going to talk about today is going to touch on the assembly portion, specifically assembly using robots. So some of the motivation for robotic assembly here, at least from my perspective, a big piece of it is this. The current practice is to use very complex deployment mechanisms. So this is how James Webb works. There's many actuators involved in this complicated unfolding process. And those deployment mechanisms add parasitic mass and additional degrees of freedom to the structure. There's each of those actuators carries mass, and each of these joints that have to unfold give you additional degrees of freedom, and the combination of those can result in undesirable dynamic modes of the structure. So those structural dynamics don't have anything to do with the intended performance of the structure. They're just side effects from having to do this deployment. So what OSAM would do is basically shift that mass and those degrees of freedom off of the structure itself and onto an assembly tool that could be reused for other missions. And in this case, the assembly tool could be a robot. So we're talking about enabling upgrades, repairs, extending the lifespan, increasing mass and volume, and being able to achieve a single structure with multiple launches. These are the big benefits that OSAM offers. So I'll give some historical context about OSAM at NASA Langley Research Center. Back in around the year 2000, there was some initial work to do a kind of this mock in-space assembled telescope assembly using an industrial robot as a stand-in for a space robot. This robot had swappable end effectors. The structure had 102 struts, 12 panels. It could be both assembled and then disassembled. It used computer vision that relied on fiducials to do visual servoing of the robotic end effector, and it had motion planning that included deflection modeling and correction for those deflections. In the intervening years, there's been a lot of different hardware developed, and I'm just going to kind of explain a little bit about some of the main, some of kind of the flagship products that we've developed. So the thing on the image here is called the Lightweight Surface Manipulation System. It's a hybrid crane and robotic manipulator designed for the lunar surface, and its main purpose would be for gross movement tasks like unloading payloads off of a lunar lander and moving construction materials from one side of a work site to another. This thing is scalable in both size and load capability. What we're showing here is called the Talisman, or Tendon-Actuated Lightweight In-Space Manipulator. So the idea behind this robot is to give comparable performance in terms of reach to the robot arm that was on the space shuttle, but it's actuated via a cable system, cable and spreader system. Basically, these cables apply a force at a moment, and that's how joint torques are produced instead of having large motors at the joints, and thereby there's a reduction, order of magnitude reduction in mass, packaging volume, and power requirements. We also have some jigging robot work. So this one here is called the NINJAR for short, NASA Intelligent Jigging Assembly Robot. This is a Strut platform mechanism. Strut platform is a mechanism that is comprised of 6 linear actuators connecting 2 plates. And basically what you can do is use the 6 degrees of freedom of each of those actuators to control the 6 degrees of freedom of one plate relative to another. Very useful for precise positioning. You can see in the image on the right, there's a truss bay built up around this robot. So the Strut platform concept will come up again later in the talk, and we'll see a little bit about how this can be used with other robots for an in-space assembly concept of operations. We've have some custom end effector design that we've done. This one is called Samurai. Basically, this is used for handing off structural struts to something like the NINJAR on the previous page. And this is how these robots would work together. So there's the Samurai end effector grabbing struts out of a quiver, handing the struts to the NINJAR, and basically it's going to fully populate the truss bay around the NINJAR. NINJAR will update its position to make sure everything is aligned properly, and we assemble one truss bay at a time, and then we weld those joints. And by the way, this is for a project called Cyrus. That was a commercial partnership with Northrop Grumman. So then after one bay is assembled, the robot comes and lifts up the NINJAR so that the next bay can be assembled. And what I just showed you was kind of like an artist's interpretation, but we did do some lab experiments And the end effector in this case is actually at the end of the LSMS robot to basically do this experiment in 1G. All right, so that's some hardware that we've developed. Now maybe this audience will be more interested in the software. So we have a communications framework called the Autonomous Entity Operations Network, or Aeon for short. It's a publish subscribe communication framework for autonomous robots based on the data distribution service standard. It's comprised of several built-in data types that for communicating common information for robot operations, like pose, trajectories, sensor signals. So we have some common sensor data types like IMUs, GPS, and LiDAR. And the value of this Aeon network is that it's a real plug-and-play architecture. So you can just put the right interface on your independent software node and plug into the rest of the system. The block diagram that I'm showing here is this system was originally designed for UAVs, like small quadcopters. So you'll see some nodes in this diagram that correspond to that, like a tree dodger node. So we've taken a lot of that initial development that was done on the for UAV applications and applied it over to this space robotics side. Our other big software product in my group is called the Baseline Environment for Autonomous Modeling, or BEAM. And this is a simulation / mixed reality environment that's built in the Unity engine. Basically, it has integration with Aeon, so we can use it for real software in the loop testing. You can have the subscriber with the exact data type that the software is publishing and get a sense of performance in a simulated environment. So not just software in the loop testing, but also visualization is a big component of BEAM. So in this example that's on the screen, we have a group of ground vehicles doing a coordinated search algorithm. So basically they're trying to cover the area of this room. And the way that this algorithm that they're following works is there are several discrete points on the ground, and the visualization on the right side shows these discrete points changing color based on how recently they were observed. So you can get a real intuitive sense that their goal here is to paint the room green and really get some insight into how well it's performing. All right, so now I'm going to dive into the project that Trevor worked on when he was an intern with us, called Assemblers. So Assemblers is a modular, reconfigurable robotic manipulator. It's composed of Stewart platform modules stacked on top of each other to build up a long reach manipulator. The idea is that the existing space robots are purpose-built and have high non-recurring engineering costs. And with a modular approach, you can reconfigure these modules to get a wide range of capabilities and eliminate the need for mission-specific technologies. And one thing that can be achieved here is the trade-off between high precision and low reach to long reach and high precision. So on the left-hand side of the spectrum is that NINJAR robot. On the right-hand side would be something like the LSMS or Talisman that I showed earlier. And maybe your specific application exists, the right point in the trade-off for you is somewhere in between them. So having this modular approach lets you optimize for a specific application. So here's what a single module looks like. We have the going from top to bottom. There's a top plate with modular connectors, a wire reel, thrust bearings, U-joints where the actuators are connected to, then the 6 linear actuators, and U-joints and thrust bearings on the other side, electrical housing at the bottom, and a modular connector at the other side of the bottom as well. All right, here's what the control architecture looks like for this system. And this is kind of the paradigm that we're using for autonomous robots. At the highest level is a task manager, which takes basically a list of tasks, a list of available robots in kind of like a multi-agent work site, and allocates robots to tasks. And in doing that allocation, it will generate trajectories to go from where the robot currently is to where the task that is being allocated is. So what comes out of this task manager are trajectory parameters, which will go into a trajectory executor system, which essentially evaluates the function using these parameters, and computes actuator commands, which go to a low-level joint controller. The joint controller interacts directly with the hardware, and out of the hardware comes raw sensor measurements, which can go back to the joint controller for that low-level control, but also into a sensor fusion system, which can provide a state estimate of the whole manipulator, and that will get used to update the task manager. And then there's 2 types of fault detection present here. There's fault detection of the robot itself, or of the module. That's what this one is. And then there's also fault detection of the assembly, and this means, again, the application of these robots is to assemble space structures, right? So components have to be properly aligned before they can be physically adjoined. And this fault detection for the assembly is basically like an alignment detector. Before we try to plug something in, we need to make sure that the robot's in the right position. If not, then we need to add a new task into the list of tasks for the task manager to correct that alignment. All right, and for any of the autonomy to exist, we really need to have good modeling and simulation. So for this type of robotics, kind of the first step is really the kinematics models. So at the Stewart platform stage, so at the modular stage, the Stewart platform is a parallel manipulator, meaning it has multiple joints connected to the same points. And for parallel manipulators, the inverse kinematics are analytically defined, but the forward kinematics need to be calculated numerically. The opposite is true for serial manipulators, which is like your one link is connected to a joint, which is connected to the next link. And if you have, I think serial manipulators are probably the more prevalent type of robot that you may have seen before. So this is an interesting point, because we really have the best of both worlds and the worst of both worlds, because at our module level, we have a parallel manipulator, and at the manipulator level, because these modules are stacked together, that forms a serial manipulator. Okay, so the module inverse kinematics, basically we have a position and an orientation of the top plate relative to the bottom plate, and we can define some vectors for where the joints are on each plate, in 2 coordinate systems, 1 coordinate system attached to each plate. And then we can just use some vector addition to figure out the vector between top plate and bottom plate. That gives us our position variable. And then the rotation between them comes from the well, that rotation is part of this vector addition. So that's in the equation that's accounted for right here with this this r from t to b. Basically, we can put those into a this equation at the bottom. We take the magnitude of the right hand side here, and that is the length of each actuator. So the question that we're trying to answer here is, given the position and orientation of top plate relative to bottom plate, what are the lengths of the actuator? That's the inverse kinematics. To go the other way, so I see a question from Robin Schmid. What sensors are you using for the state estimation, LiDAR vision, and IMU? So at the module level, there's an IMU attached to each plate, which provides an orientation estimate. Then let me go back a step here. Each one of these actuators has a potentiometer attached to it, which can tell its length. So using this kinematic model, we can use all of those lengths to get an estimate of the top plate, and then refine it using the IMU. And there's also one additional sensor, which is a string potentiometer that connects the middle of the plates as an additional source of position feedback. So really the main source of information is the potentiometers in the actuators, and then it can be refined with those that IMU and this string potentiometer. And that's just for this application. Towards the end of the presentation, I'll show some current work that uses more vision type approaches. Okay, so for the forward kinematics, we have to define an error function. So it's going to be an error between the lengths that we are given and lengths returned by the inverse kinematics model. And there's some constraints, like the quaternion has to be a unit quaternion, and the lengths of each actuator can't exceed some limits. And then this inverse cosine function at the bottom, this is a constraint on the angle between the actuators and vertical. So constrained optimization gives us the forward kinematics. Right, and this is just a very simple animation to show that these kinematics functions are working. So we specify a trajectory in the top plate space, use the inverse kinematics to find the actuator lengths at each time step of this animation, and then use the forward kinematics to generate the animation and essentially the top plate is in its commanded trajectory, just going in a circle, remaining constant. Okay, then when we get to the manipulator level, so I already touched on this, but the opposite case is true, where the forward kinematics now have the analytic solution and the inverse kinematics require optimization. So for the forward kinematics, we can build them up in a loop, and this supports the modular approach. So how many iterations of this loop you do depends on how many modules are in the manipulator, and we are basically just doing transformations along the way until we get to the end effector. and return the position and quaternion for the end effector. I see a question from Hossein. What is the future of this technology / concept? Yeah, the future is that OSAM is really a new paradigm that will enable a lot of missions that can't be done right now, like very large telescopes, lunar construction, so setting up infrastructure on the lunar surface, as well as extending the life of platforms to have persistent platforms in low Earth orbit, for example. A second question, which of the fields are involved in this concept from engineering? Mechanical engineering, civil, or electrical? There's a little bit of everything. That's a great question. There's definitely a little bit of everything. And what I'm talking about right now is kind of a blend of, this is mostly mechanical engineering. I'd say that I'm discussing right now, but there is certainly a lot of computer science for setting up the communication frameworks for robots, mechanical engineering for designing structures to be assembled, civil engineering when we get into the idea of lunar surface infrastructure, civil engineering to kind of understand how the lunar soil plays into this. Yeah, there are a lot. I guess I didn't say what my background is before starting this, but I studied control engineering in grad school, and a lot of my work has branched off of that foundation. Okay, so these are just some examples to show the inverse kinematics used to put the manipulator in various poses. So this is a 4-module manipulator in each of these images. All right, and then at the next layer down for modeling, it's important to know how the actuators behave themselves. So there's a lot of times you'll find spec sheets for off-the-shelf components, and here we have we can look at how the nominal speed for these actuators depends on load. This is important for knowing that we don't overload the robot, and this gets used in trajectory generation. I'm just going to take a peek at the time here. Okay. Okay, these are some slides that are going to be familiar to Trevor. So we also modeled the mass properties to account for loading on the robot. Basically, we can have basic building blocks for each of the components, like the actuators here, and combine them together to build an overall mass model so that we can calculate dynamic loads to support trajectory generation. There's also a modeling effort to understand end effector error. So each sensor is going to have some noise in it, and it's important to understand how that noise affects our knowledge of the end effector position. So we had an effort to do some Monte Carlo analysis and also analytical analysis for understanding the uncertainty. And this is actually what Trevor worked on when he was an intern with us. So abstracting out a little bit from the kinematics models I was talking about, you can basically represent the end effector variables as a function of joint variables. And we can take the derivative of that function, and that function is what, the details of this function were on the last couple slides. And that gives us the manipulator Jacobian. And the Jacobian will show us how the end effector variables change with respect to small changes in the joint variables, which you can consider to be the noise in the joint sensors. And then for small movements of the joint variables, it's a linear relationship, and thus we can use this equation at the bottom to relate the joint covariance. So that's basically a diagonal matrix where each element is the variance of each sensor, and we can get a covariance matrix for the end effector variables as a result. So this is kind of the analytic way of looking at it, and Monte Carlo sampling would be the numerical way of looking at it. Using that joint covariance, we can get a uncertainty ellipsoid for the end effector for a given probability threshold. What I'm showing here on the figure on the top is just like a stick model for the Talisman robot. And if you look closely, you might be able to see it. There's a little blue dot at the end effector, and zooming in on it is what's in the image below. So the points represent Monte Carlo sampling, and the ellipse that's drawn is the covariance ellipse. And this just shows that they match. And the real purpose of doing this kind of analysis is to ensure that any capture envelopes relevant to the ConOps of the robot are, and ensure that those capture envelopes are bigger than the uncertainty, so that you know that you're inside the envelope that you need to be to interact with an object. Question from Ollie House. What is the advantage for the modules to have parallel kinematics? The advantage is to have more precise movement at smaller at smaller size manipulators. That's the reason that we designed this for to use Stewart platform modules. I see a question from Theo Schaefer. Is this for in-space or on-surface manipulation? Do we have to take gravity into consideration in the equations of motion? This is... So what I'm talking about right now is the assembler's manipulator was really designed for the lunar surface. Yes, gravity matters there. And that will come into play if I get into trajectory generation. In fact, I might, in the interest of time, I might skip ahead a little bit. I'll just show kind of some of the results of this Monte Carlo sampling. So we can change joint variables and see how the end effector variables change here and get a sense for what is the uncertainty. Yeah, since there was a question, I'm going to skip ahead to trajectory generation, and also in the interest of time. So to generate trajectories for any size manipulator, the inputs are the end effector goal pose and the starting actuator lengths, and the output is a collision-free trajectory in the actuator space. So what we need to have here is the inverse kinematics in order to determine the goal actuator lengths from a goal end effector pose, a path planner that gets you from point A to point B, and that path planner has a collision checker to make sure that each step along the way is collision free and doesn't violate any of the kinematic constraints. Goal checker to see if the to make sure that you've reached the goal. And then what's kind of interesting to that question that was posed is this spline function that fits a polynomial spline through each point with continuous jerk, third derivative of position. So this spline function will output at first a normalized time path or a normalized time trajectory. So we just assume that it starts at time equals 0, ends at time equals 1. And then we have to use the dynamic constraints of the robot, which come from the actuators, like how much load can they carry, combined with the payload. So we have to, given a payload, we have to know what the static loading is at each point in time, and also the dynamic loading. So the static loading is what comes from gravity. That's trying to link back to that question. The static loading comes from gravity, but there's also a dynamic loading, which comes from how fast is the actuator moving. So a few demonstrations here of the different components of trajectory generation. So we have to represent objects as meshes in order to do the collision checking. And we have a collision query algorithm. It's called the Gilbert-Johnson-Kearthy algorithm. Basically, this gets ran at each sampled point in the path creation, and then on the right shows a path that is moving around an obstacle from this path generation. Okay, so let me see, check time again. So my time is view is behind my screen that I'm looking at, so that's why I'm leaning over. So here's how our low-level joint controller works. There's basically two components, a feedback component and a feed-forward. The feedback component is just a proportional control on the length of the actuator, and the feed-forward component tries to use the properties of the actuator to match the commanded velocity of the trajectory. So this gain that's applied for the feed-forward term, kV times kf times v nom. So kV is a voltage gain, which it just has to do with how fast we want to move compared to what happens at 12 volts. Kf is the load gain, which is how the nominal speed of the actuator changes depending on the load. So we need to know the expected load at each time step for the controller as well as for the trajectory generation. And that's essentially how the low-level control works. Feedback on position, feed forward on velocity. Just some simulated results of tracking a commanded trajectory here. On the left-hand side is the length, and on the right-hand side is actuator. So at least in our simulated environment, we can control with this architecture. These are the actuator voltages on the left and the actuator loads on the right for the same scenario. And you'll notice that this actuator 4 that I'm circling with my mouse gets saturated at one point, and there'll be there's some upcoming slides that show the effect of that. We had a question about sensor fusion earlier, so here's the sensor fusion system. Uses these sensors, the IMU, and from the IMU we care about gyroscope and accelerometer. There's the central string potentiometer and the individual potentiometers in each actuator. And we combine those using an extended Kalman filter. And the estimates that we produce from that are position and orientation of top plate relative to bottom plate. Okay, so here's some more charts that we can just look at quick. So on the left is the generated trajectory, and this is the same scenario that I just that I was showing earlier. And on the right is the top three are the angular rates: roll rate, pitch rate, yaw rate of the top plate. And the bottom three are the roll angle, pitch angle, yaw angle of the top plate. And the takeaway here is that there are multiple signals plotted, but they're all on top of each other, so we're able to estimate successfully. And these are some more charts from the same example. And on the left we have accelerations, and on the right we have velocities. And this kind of jolty acceleration, this is the point in the trajectory where that one actuator was saturated. So you can see that the estimate is smoother than the actual acceleration. So that tells you something about the bandwidth of this estimator. And most of the time, operations will be slower than this. So not a big deal. And then lastly, the estimated positions. All right, so we finally, after doing all that analysis work, got to building an actual robot and testing it in a lab. So this is a video of one of the trials that we did. It doesn't do too much. We just move it into some commanded pose here, and then move it back. But there was a hardware component. It's always a fun time seeing the things that you worked on like paper and in simulation for so long becoming real objects. And that's me over with the hard hat over there. And we're using, you might recognize there's a motion capture system around these cameras, and these silver balls attached to the top plate are markers to get picked up by that motion capture system. And we were trying to see how well the sensor fusion system compares to an external measurement here. Okay, time check. All right, got a few minutes. So, okay, this is, yeah, we'll talk about this fault detection. So I mentioned earlier there's a fault detection system that tries to detect alignment of two components to be joined. So we trained a neural network classifier using synthetic data, synthetic images that came from CAD models. On each of these images on the screen, at the top of the image is the receptacle, and the bottom of the image is the strut. And so these have to be properly aligned as they are in the right image. Otherwise, we cannot join them. If you attempt to join, it will fail. And the capture envelope for this is given on the slide here. So if we're not within those tolerances, this fault detection system should detect this as misaligned. So we base this on, are the results published as a paper? Hossein, there is a paper that we published that is kind of like an overview, kind of like it's kind of as much detail as are in these slides. It was in the AIAA SciTech forum this year. I can, let's see. Not sure what the best way is to distribute a link, but we can do that. We can do that somehow. So yeah, machine learning classifier trained on synthetic data. We use the SqueezeNet architecture implemented in PyTorch. And the reason for using SqueezeNet is to be able to run this on board the robot at some point. So we got a So what I'm showing here is accuracy over training for both the validation set and the training set, and then the loss over training for validation and training set. And the ultimate test accuracy that we got after that was 96%, which was within our pre-decided KPPs. Looks like somebody might have found the link. That's great. Okay, so I'm gonna wrap up soon with one last topic to talk about, and that is our a project that's currently underway, called the Precision Assembled Space Structure Project. So a couple years ago, there was a study performed across with many government, industry, and academia entities to look at the value of an in-space assembled telescope. And the image on the left is the concept that they came up with. And the video is a simulated assembly of this mirror structure in a lab that we're currently renovating to become like the next, the new NASA Langley in-space assembly lab. So we're going to develop technologies to demonstrate the assembly of this telescope concept. The first stage of this is to put 3 truss modules together. And so we've done path planning for that. And there's relevant capture envelopes. We have to first pick up this tool, then use the tool to pick up the truss, and then align the truss with the next one to be joined. Close-up views of the tool and the capture envelopes here. So one new technology that we're developing here is object pose estimation just from visual RGB images and point clouds. We're combining those 2 sources of data and using that as a visual servo sensor. So the idea is just from the robot kinematics and the joint sensors of the robot, you can get to some like a nominal position, but that the uncertainty in that end effector placement may be outside of the capture envelope that you need. So this additional visual servoing maneuver can help close the gap. So the way this works in a loop is this object pose estimation will give you a 6 degree of freedom pose between the end effector and the object. That'll be used in a visual servoing control law to update a commanded position, and a camera/LiDAR sensor will put out an image and a point cloud to go back into the object pose estimation. The architecture for this object pose estimation is we take a RGB image, we run an object detection CNN, we get out a mask or at least a bounding box of relevant pixels for that object, and then we deproject those pixels onto the 3D point cloud. And then basically we have a point cloud of the object as it actually is in the real environment, and we have a CAD model that we can position and rotate to align with that point cloud data, and the alignment that minimizes some cost function is what gives you the pose estimate. So we've done some initial training using MaskR CNN, done some initial real crude benchtop testing here using a tape measure, so that the tape measure and the algorithm matched pretty well. So that motivates the more comprehensive uncertainty analysis, which we're going to be doing shortly here. Some notes on the testing approach. I'm going to move to wrap up now, I think, because I'll save a little bit of time for questions. So once we do that testing, we'll have to corroborate so we're going to test with synthetic data so that we can get lots of points. And then we need to make sure that the synthetic data is reliable using some kind of test rig. All right, and that is what I have to say about autonomy for on-orbit servicing, assembly, and manufacturing. Thanks everyone for listening, and yeah, we'll have some time for questions. See, Carthy says, John, you're explaining the uncertainty principle well. Keep it up. Well, thank you. I appreciate it. Let me see here.
Hey, John, it's Trevor.
Hey, Trevor.
Thanks a lot for the presentation. It was really cool to see some slides that I've already seen, but also some new slides that show all the progress that you're making on this. And
some that you made.
But a lot of progress since then, so it's really awesome. I had a question about the interactions between those different Stewart platform arms. So you talked a lot about how a single arm works together, the kinematics and the control and the planning. But I guess there's also a really big component about these arms working together. Could you elaborate a little bit more on what's the general problems and what have you discovered about that?
Yeah, the general problem is that if you consider if you consider multiple robots operating in the same workspace, you have to avoid collisions with each other. The way that collision avoidance works in like the at the basic level of these path planning algorithms is to have kind of a static scene at each time step. So that assumes that you know the position of both manipulators, right? So you'd really have to consider them as you really have to consider the entire thing as one robot and do that path planning simultaneously, which will be computationally expensive, especially when you start thinking about how these kind of concepts scale to include lots and lots of robots. So it's not something that we've really that is not solved. It's not something that's solved. But there are ideas afloat, including using like artificial potential based approaches to kind of like steer robots away from other robots. Yeah, it's a big open question. I'll say that's probably where I can leave it for now.
I can imagine it's quite complicated. We have another question now. Let's see. How do you compensate for material deformation due to heat, such as welding?
That's a good question, and the best answer I can give is so okay. Let me go back to the beginning, because now oh wait a minute, this assembler's conops, that alignment detection that I showed towards the end there is, I mean, there's no welding here. This is just a mechanical connection, purely mechanical connection. But I did show early on this Cyrus concept that did include welding here. If you remember, let's see if I can get to the point where the weld happened. There we go. So in this concept, there's this intelligent jigging robot in the center of the truss bay. And the reason to have this is to make fine corrections to the position of the ends of the struts so that this welding can happen. So once one side is welded, if there's a deflection in the next side, the one that's about to be welded right now where I paused, this robot still has the ability to make adjustments. So this is one thing that we've designed that does account for that that potential.
Okay, and we've got another question from John Luca. Is a version of this system already planned, or is it too early in development? So kind of what part of the project are you in right now, and do you think it'll be on the moon or in space soon?
So nothing that I've talked about is nothing that I've shown you guys today is planned to fly yet. Still too early in development, but there are 2 existing missions that are going to fly to demonstrate OSAM technologies, and they're called OSAM 1 and OSAM 2. And so pretty easy to remember. So OSAM 1 is a mission to refuel a satellite that was never designed to be serviced. That mission is ran out of Goddard Space Flight Center. So that's a lot more on the servicing side of the OSAM acronym, but a lot of the same ideas apply. So they will have a robotic manipulator that's going to cut away an insulating blanket and insert fuel into this satellite that's at the end of its life. Right now, that's really like the flagship OSAM mission. The next one, OSAM 2, is it's a mission that's in partnership with industry. The company that is leading it is called Redwire Space. They used to be called Maiden Space. They are going to be assembling some kind of structure very similar to what's in this video. So it's not using these exact robots, but a very similar concept. And that OSAM 2 also, you can find information about it under the name Archinaut 1. That's the internal Redwire name for it.
Thank you. Okay, we have might be the last question now. It's about the acceleration measurement from the IMU in microgravity. How does microgravity affect how you use an IMU? Is it even useful in space?
Yeah, that's a very good question. So we're actually not using the acceleration measurements for orientation, but we are using it as like a correction for position. So we're using it while the robot is in motion, integrating that acceleration in the extended Kalman filter. So actually, I kind of glanced over some of the details, or maybe I didn't have details on the slide, but everything that's estimated in this EKF includes acceleration velocity and also rotational velocity, and then the things that we really care about are position and orientation, but those things get integrated from those higher derivatives. So yeah, not useful for the orientation, but useful for the position.
Makes sense. Okay. Okay, we have one final question. I think we'll wrap it up after that. Is there an assembly mission scheduled for the Artemis program?
That is a great question. And the Artemis program is there are a lot of pieces in it, and ultimately the vision is a sustained human presence on the surface, right? And in order to have that, we will have to erect infrastructure. So that's kind of like in the 2030s timeframe. But in between now and then, there's a series of missions called CLIPS. It's CLPS. There's no vowel in there, but it's pronounced CLIPS. And I think there is some CLIPS mission that's going to have some kind of assembly demonstration. I don't have the details for it at the top of my head, unfortunately, but if you want to look into what the CLIPS missions are, that might be the starting point.
Okay, thanks a lot. Thanks for answering the questions, for the presentation. It's really interesting work what you guys are doing, and thank you for those listening. If you like this talk, we're doing another talk with a NASA speaker on April 2nd about the James Webb Telescope. This is going to be with Dr. Cataldo, who's the mission chief engineer. And yeah, thank you for joining. Have a nice evening or a nice day, wherever you are.
Yeah, well, thank you so much for having me. Thanks for the invite, Trevor, and thanks to everyone for attending.
Google Developer Student Clubs train hundreds of thousands of university student developers globally while having fun getting to know other students at their school. Google selects students with strong leadership skills from across the globe once a year to start a club on their campus. These leads believe knowledge is power and that technology can do extraordinary things for the world. They take on the responsibility to help students learn and empower each other to solve real problems around them. Students can participate in the annual Solution Challenge by Google developers to solve for one of the United Nations Sustainable Development Goals. Join us in building a global community for students in technology.